The Samoan Passage, below a deep ocean choke point between the North Pacific and the South Pacific, seen as a vital part of the Earth's climate system. In early 2014, the APL-UW team known as the Wave Chasers returned for the third time in 3 years to the Samoan Passage to learn more about the massive amount of water churning through this ocean abyss 5,500 meters below the surface.
In the Samoan Passage abyssal mixing experiment, we were studying the flow of Antarctic bottom water through a passage just north of Samoa, just before it crosses the equator. So this is water coming from the south, flowing along a boundary current along the western boundary of the South Pacific, and then getting constricted in a small passage and flowing into the North Pacific.
Most people think of the deep abyssal circulation as sluggish. Now, we've known that it's not the case in some specific areas.
It's just one of these incredibly special places in the ocean where you can measure the incoming properties of the fluid and measure the outgoing properties, and there really is just a big measurable difference, and we know that that's because of mixing. And the big contribution of this experiment is that we actually measured how much mixing there really is.
In this project, we had 3 cruises total. The first cruise was a mapping cruise where we wanted to scope out the geometry of the Samoan Passage and really figure out what the details of the separate connected passages are. The second cruise was to deploy a mooring array that had been done 20 years earlier and measure the transport through the passage, as well as to map out the flow pathways through these connected passages. The third cruise was to focus on the processes that were driving the turbulence and the flow constrictions. A lot of these flows can be seen a little bit like a flow in a river, where you have a rock in the river and the flow goes over it and it causes a hydraulic jump or a wave behind that flow. We found some real surprises about how the flow is kind of diverted around these bumps.
You can imagine this river, this undersea river of water, and we think of it as 35 Amazon rivers worth of water that's going northward through this passage. But the passage is so complicated, and it's three-dimensional, and it really looks like the Grand Canyon. There's no single path through it, so it can go left, or it can go right, or it can go over.
So especially on this last cruise, we knew we had several locations that we wanted to focus on that were sort of hot spots of mixing. So we did several cross-stream tow-yos, we did some along-stream tow-yos.
Just so you know, tow-yoing is basically, it's like a yo-yo with a CTD. You're moving this instrument up and down, but you're towing it, so you're moving it through the water as it moves up and down. So you're tracing kind of a sawtooth pattern through the water as you steam along.
And we deployed moorings in different configurations in key locations within the flow that would tell us where the most mixing was occurring, or how the mixing and the flow pathway was determined. This Antarctic bottom water is of interest because it's the main supply for deep water in the Pacific Ocean. And there's no deep water created anywhere in the North Pacific, and so all of the water in the North Pacific at the bottom has to have come through this pathway.
Trying to figure out how to parameterize those processes in global climate models is going to be key to really correctly accounting for how this very special region modifies ocean water as it goes through there.
Science at work for you. This is APL, the Applied Physics Laboratory at the University of Washington in Seattle.